So I'm supposed to talk about chemical problems, and I'm always embarrassed by the fact that I don't know very much chemistry, even in the chemistry department. But I'll give you some flavor for this in any event. Let me just say a few words about what we do in statistical mechanics in chemistry in Toronto to give you some of the flavor for the background that the students have. We have an introductory course, a graduate course in statistical mechanics that covers equilibrium and non-equilibrium statistical mechanics. It's standard, starting with ensemble theory, Boltzmann equation in terms of dynamics, and Brownian motion and Fokker-Plonk equations and linear response theory at elementary level. We also have several special topics courses in statistical mechanics. They vary from year to year. They typically cover problems like Markov processes, a more detailed treatment of Brownian motion, stochastic differential equations, sometimes Monte Carlo methods and molecular simulation, and quantum and classical linear response theory. We also have a course that's devoted more towards high energy functional approaches. In fact, this course is done jointly with physics, and it concerns basically looking at phase segregation processes, typically for conserved and non-conserved order parameters, and then going into the regime where there are no free energy functionals in non-equilibrium systems, looking at amplitude equations, and things like the Ginsburg-Landau equation, front propagation, reaction diffusion, and so forth. We also have a related course in thermodynamics, a graduate course that goes beyond the elementary ones. It's typically divided into 4 parts. One part deals with various formulations of the second law of thermodynamics, especially the Karathia-Urey formulation, and then interface and surface thermodynamics, and thermodynamics is critical phenomena, and the last part deals with non-equilibrium thermodynamics. So these are, I think, exactly what you would find in physics courses. The difference is that the applications are slanted towards chemical problems. So that's basically the background for what our graduate students in physical chemistry and chemical physics in particular have. So like many of you, I was puzzled about what to talk about in terms of applications of statistical mechanics to chemical problems. There's really one obvious choice for this location, and that's to deal with the statistical mechanics of this process. And there's actually a lot of statistical mechanics that goes on in terms of these the steps of the fermentation process, particularly involved in these enzymatic reactions. However, I'm not going to talk about this. Instead, I'll switch to something a little more prosaic. So, what I'm going to be talking about are a problem that fits very well with some of the things that we've heard about today, both in terms of Udo's talk about the non-equilibrium fluctuating thermodynamics and the applications to molecular machines, and also to Cecil's talk, the last talk, where he discussed various non-equilibrium processes involving the fluctuation theory and so forth. It also fits very well with some of the student talks, because what I'm going to do in today's talk is something extremely simple. In fact, it'll be almost embarrassingly simple to you, but underneath it there's actually a lot of tedious algebra that I won't show you. And instead I want to just illustrate how a couple of basic concepts in statistical physics can allow you to learn a lot about synthetic nanomotors. And I'll skip basically the harder details that underlie it. And so, in order to do this, I only need a couple of concepts which have actually been reviewed in earlier talks. And that's some basic notions about fluctuating thermodynamics and about Langevin equations. And that's almost all you need to know. Of course, there's a hidden part about stochastic thermodynamics on surfaces, which you'll see. And so I'm going to start, as the slide says, with 2 slides showing exactly what things you need to know in order to follow the rest of the talk. The first one is just the idea of linear fluctuating thermodynamics. So just to set the perspective and the notation for what I'll use later, we have some thermodynamic variable x, alpha, and its flux j alpha, and the usual Onsager linear law relates the flux to the driving force for the process, which is the affinity, and an Onsager coefficient that gives you the linear response to that driving force. In fluctuating thermodynamics, you supplement that with a fluctuating flux. And the fluctuating flux satisfies a fluctuation dissipation theorem whose prefactor is given by the sum of the Onsager coefficients. And the important thing that will play a crucial role in everything that I'm going to say later is the concept of microscopic reversibility. And as a result of microscopic reversibility, I think you all know that the Onsager coefficients satisfy the Onsager-Casimir reciprocal relations, where epsilon alpha and epsilon beta take the values plus or minus 1, depending on the parity of the variable in your time reversal symmetry. And so the processes that I want to consider will have to satisfy microscopic reversibility, and we'll see the consequences of that later. The other object is very familiar. We've seen it many times, and that's the Langevin equation. I just want to make a couple of comments about the Langevin equation here. It has the form that you're all familiar with: a frictional force, a fluctuating force that satisfies a fluctuation dissipation relation, and I put it in an external force. I won't go through the details of some of the background behind this equation. I'm not talking about the historical background. I'm talking more about the details of how one establishes such an equation from a fluctuating thermodynamics perspective, because it actually plays a crucial role in everything that I'll say later, but I won't give you those details. But just in a few words, the fluctuations of the Brownian particle, as you know, are driven by the fluctuations in the surrounding medium. And so the way one establishes an equation of this type is by computing the force on the Brownian particle simply by integrating the fluid stress tensor over the surface of the particle. But the fluid stress tensor itself has a fluctuating component. And so the fluctuations in the fluid actually drive the particle, and from the fluctuation dissipation theorem in the fluid, you can derive the fluctuation dissipation theorem for the particle. And so what's crucial about this is the boundary conditions between the fluid and the particle. They play a crucial role. Typically one assumes stick, but it could be partial slip, and that in turn determines the nature of the friction and the fluctuating force. That's the idea that will be used later, but again, as I said before, I'll mention in words how it, the important points, but I won't focus on the details. Just for future reference, you all know the Einstein relation, so sometimes you'll see the friction coefficient and sometimes you'll see the diffusion coefficient in the equations. So the subject of the application that I want to discuss are synthetic motors. And these are very simple motors, in contrast to most molecular machines where a chemical reaction like the conversion of ATP to ADP induces a conformational change in the motor that leads to directed motion. In these motors, there are no moving parts, and they instead work by the fact that there's an asymmetry in the catalytic conversion of chemical species into each other on the surface of the motor. So these motors have small sizes, again, on the order of a micron, even much less, on the order of a few tens of nanometers, and they are subject to very strong fluctuations, as we saw in the last talk, for particles on this scale. The first motors were constructed about almost 15 years ago in Penn State and also in Toronto, in Ozen's group and in Malouk and Sen's group in Penn State. They consisted of bimetallic rods. One side was typically platinum, the other was gold, and they put it in hydrogen peroxide. A chemical reaction occurred, converting hydrogen peroxide into its products, and this ultimately led to motion of the motor. You can make a lot of versions of these motors. Another simpler version is just to take two linked spheres. The spheres could be, for instance, silica and platinum, and again, a catalytic reaction would occur on the platinum end, giving rise to an asymmetric catalytic reaction, and you could see the motion of the motor. So this is the actual experiment done on a silica platinum motor. These are experiments from Ozen's group probably almost 10 years ago. And you can see that the motors move with speeds on the order of 10 micrometers per second. This particular motor is pinned to the glass substrate and it undergoes active rotation with a period of a few hertz. So these are the types of motors that we're interested in.
Can you tell us something more about what is the force? What is the origin of the force?
That's my next slide. Almost next slide. Here it is. So now I want to give you a physical picture of the mechanism that underlies this, and then I'll convert it into a description in terms of the Langevin equations. So the simplest motor that's most popular for study now is the Janus motor. So it's a spherical colloidal particle, again with dimensions on the order of microns or submicron. Consists of a catalytic part in red and a non-catalytic part in blue. And again, as in the previous case, I've written these as irreversible reactions, but they're all reversible reactions on the surface of the motor. And on the non-catalytic end, of course, the system is chemically inactive. So you have two solute species. A fuel would be the product, and these species typically interact with the motor or the faces of the motor through different intermolecular potentials. So you can see that if you generate a concentration gradient as a result of the catalytic reaction, then because of the fact that the species interact with the motor through different intermolecular potentials, you'll generate a body force on the motor. Now, the system is force-free, and this outer region, I'm assuming that the particles interact with the motor through short-range potentials, and the outside of this region, if you include the fluid plus the forces on the particle, the system is force-free. So the body force has to be compensated because of momentum conservation to flows in the surrounding fluid. So the chemical reaction then couples to the fluid velocity field, and in fact you generate a velocity field in the vicinity of the motor that looks like this picture. You're seeing the streamlines of the near field velocity field that are generated by the coupling. So this is a nice problem of chemistry coupled to hydrodynamics, because the chemical reaction is responsible for producing the body force, and this chemistry, the chemical reaction on the surface of the motor, produces a flow, coupling through the pressure field, that gives rise to a slip on the surface of this boundary layer, which then serves as a boundary condition for solving the Navier-Stokes equation for the surrounding fluid. And the motion of the motor occurs because of the coupling of the fluid flow to the motor. So actually, if you look far from this, the flow is actually inward, outward. So this is basically the mechanism that is responsible for the motor motion. And what I'm going to talk about, even though I won't go into the details of it, is the case where what's called a thin layer approximation, where this boundary layer is shrunk onto the surface of the particle, and the effect of the boundary layer and the processes that occur in the boundary layer are accounted for in effective boundary conditions on the surface of the particle. So just like the Brownian motion, where you have the fluid velocity field either sticking or partially slipping on the surface of the particle, in the case of this reactive system, you have to take into account the fluctuating chemical reactions on the surface of the particle and how they couple to actually the velocity slip in this picture. So those are some of the details that I won't go through in detail, but I want you to keep in mind that those are the processes that underlie the description. So, with that in mind, I want to make a couple of other points about this. So, I mentioned that the chemical reactions, just because it's the true dynamics of the system, must be microscopically reversible. So, if you take a Janus particle of this type, you allow the chemical reactions to occur in an equilibrium system, you're not going to get any motion. You can't have any net motion in the system. The forces adjust themselves so that the particle simply undergoes Brownian motion. So in order to, like all of these molecular machines, you have to drive the system out of equilibrium in order to get the directed motion. And in this case, the way it's driven out of equilibrium is to couple the system to reservoirs. In this case, the reservoirs have fixed concentrations of the fuel and product species. So, on the surface of the motor, you have some mean reaction rate. For this simple reaction, it's forward rate times the concentration of A minus the reverse rate times the concentration of B. So this is the production of B in the system. And at equilibrium, you can see that this will vanish just by detailed balance. So by coupling it to these reservoirs, you actually introduce a chemical potential difference in the system that's the driving force for the reaction, and that's indicated by A, the chemical affinity for this case. And as this form, so you can see at equilibrium, the affinity is 0. And so this is the thermodynamic driving force for the reaction, and that's what's basically responsible for the non-equilibrium effect that leads to motor motion. So now we want to, just on phenomenological grounds, although one can actually derive this equation using the techniques that I just mentioned, write down a Langevin equation that describes this picture. So it's exactly the same as Brownian motion with one additional term, and that's the diffusio-Faradic force. And the diffusio-Faradic force is simply the force that's responsible for the process that I just described. And this term naturally appears in the Langevin equation. If you carry out a derivation the way I described, you would do exactly what you did for a Brownian particle. The only difference now is that you have a modified boundary condition that accounts for the coupling of the reaction to the slip velocity on the surface of the particle. And just carrying out the algebra, you find an additional contribution that's the origin of the directed motion for the particle. So this is what you would guess for a Brownian particle. I think that is undergoing active motion. Now, just to be more precise for what we're dealing with, as mentioned several times before, these are small particles, And the inertial term really can be neglected in these systems. So if you look at the Reynolds number, I mentioned that the velocity of the particles are typically on the order of 10 micrometers per second or so. The radius is about a micron. If you use the kinematic viscosity for water, you find 10 to the minus 5. So you can drop that term, and from now on I'll be dealing with the overdamped equation. And so instead of the diffusiophoretic force, you have the diffusiophoretic velocity, which is just the force divided by the friction. And I've noted here that the force, just by symmetry of this particle, is directed along the axis of the particle, just by symmetry. Now I've written the reciprocal of the friction as beta d, and then you have the fluctuating velocity. So this is the Langevin equation. If you look at the literature, you'll find that people have written down this equation many times in describing active Brownian particles. For diffusiophoresis, the velocity takes a specific form. Often it's just a prescribed velocity in some models, but here it actually has a specific form that depends crucially on the concentration gradients that are set up in the system. But nonetheless, I think this equation is very plausible on physical grounds, and not many people would doubt it. So,
is there an extra contribution to the fluctuating force?
No, the fluctuating force is exactly the way it is here.
It's not affected by.
So, as you mentioned, the diffusible velocity is essentially related to the value that you fix on the chemical potential of the two species in after equilibrium.
Exactly, it is. Yes, in fact, if you look at the expression for this, it's related to the gradient of the concentration field averaged over the surface of the particle, which in turn can be re-expressed in terms of the affinity.
Do you need the equation for U?
Where's U?
Use it.
Yes. U. Yes. So U satisfies its own Langevin equation, and for a spherical Janus particle of the sort, it decouples, but it's an equation that is nonetheless there. So I'm neglecting it, I'm not showing it in what is here because it's sort of a trivial equation, but it's crucial because it means that the motion will ultimately be diffusive on long time scales.
Just because this term that you use, indeed, you might obtain also with the temperature, standard temperature gradient, because your chemical potential depends on temperature. So actually, this goes also with thermal diffusion, no? Thermophoresis, no?
Oh, yes.
Because you might have the same effect by assuming that your chemical potentials depends strongly on temperature.
I forgot to say. So we're considering the case where the reactions are thermoneutral, and so we're not including any thermophoretic. It's very easy to include thermophoretic effects,
absolutely.
But keeping things simple.
The treatment, yes, is interesting. Yeah.
So just to be a little bit pedantic, it's necessary. I want to rewrite the Langevin equation in a way that involves the driving forces for this reaction. So this is a copy of the equation I showed earlier for the linearized fluctuating thermodynamics. And in our case, the thermodynamic variable is the position of the Janus particle. And we have two driving forces for the reaction. One is the chemical affinity that I wrote down later that determines how we're driving the reaction out of equilibrium. And if we have an external force on the system, we have a mechanical affinity as well. That's just force divided by kT. So I can rewrite the Langevin equation on the previous slide in a form that explicitly involves these two affinities. And for the mechanical affinity, the prefactor is just the diffusion coefficient, and that's the first Onsager coefficient. And for the diffusiophoretic velocity. As I just mentioned before, it's proportional to the chemical affinity, and here I've rewritten it by pulling out the chemical affinity and the prefactor, whose form we don't have to worry about right now, and that defines the second Onsager coefficient in this expression. Okay, so that's looking at the motion of the Janus particle using a simple Langevin approach. The other part of the story is the chemistry, because all of this is driven by the reactions that occur on the surface of the particle. And so those reactions are also fluctuating quantities on the surface of the particle. So now we need to consider the Langevin equation for the reaction rates. And so, again, based on almost phenomenological grounds, although you can derive this as well using the same fluctuating thermodynamics approach that I mentioned, we can write down the equation for the reaction rate, and I'm defining that now as the number n of product molecules produced in the time t, and that consists of two pieces. One is the mean reaction rate that I wrote down earlier, and the fluctuating contribution to the reaction rate. And this fluctuating contribution satisfies the fluctuation dissipation theorem, and instead of the normal diffusion coefficient, it involves a reaction diffusivity. And so, again, this is an equation you can derive, but you can also just guess on phenomenological grounds. Just as for the Langevin equation, I can write this in terms of the affinity, the driving force. The driving force is, again, the chemical affinity. And it turns out, with a little bit of algebra, that you can write the chemical affinity close to equilibrium as the ratio of the mean reaction rate divided by the reaction diffusivity. So the prefactor of the driving force is the reaction diffusivity, and that gives me another Langevin, another Onsager coefficient for this process. So those are the two equations that we have so far describing the system. So if you put those equations together, you see something's wrong. You have a pair of coupled Langevin equations. You don't satisfy the Onsager-Casimir relations. So that means there is a missing term here that is the analog of the diffusio-Ferretti coupling in order to satisfy the Onsager-Casimir relations, because both of these variables are even under time reversal symmetry. So what you're led to by just the time reversal symmetry properties of the system is that the equations must look like this. So there's an additional contribution if you have an applied external force that changes the reaction rate of the system. And so these fluctuating forces are coupled and satisfy a fluctuation dissipation relation that's consistent with the fluctuating thermodynamics formulation. So one of the implications of this is that the reaction rate now depends on the external force. And this actually makes the problem completely analogous to what Udo said yesterday about molecular machines. If you take the ATP synthase motor and you consume ATP, you can make the motor turn, but if you apply a torque, you can actually generate ATP. So in this case, for these diffusio-Ferretic motors, if you, under the right conditions, apply an external force, you can actually make the motor move backward and generate fuel from product, net fuel from product. You should stress that this is a linear theory, so you have to work close to equilibrium to find the reversal, but nonetheless, the effect is here.
So you can really observe this very nicely, that deviations from, or produce a situation where quite far from reality that you observe a very strong violation of all that.
So to answer your question, in order to, I think that if you apply an external force to the system, even if it is far from equilibrium, you should be able to see the fact that the reaction rate depends upon the external force. To actually synthesize fuel from product, the theory applies only close to equilibrium, so you have to adjust your external drive to make sure the system is very close to equilibrium, and then you'll see it. Otherwise, nonlinear effects come into play. And in fact, we don't have a theory for those, but we have simulated them and we know what they look like.
And so there is a way at least to simulate and have an idea of what's going on in that situation.
Yes, right. I'll show that later, actually.
Do I understand correctly that this calculation force W, so in the second, in fact in both probably, there is also, they include also the noise in the axis of the particle, so that is fluctuating as well. Right?
Yeah, I mean the orientation.
So it's included in those. So
there should be a third equation
right.
here. The third equation is independent of these drives, and it simply causes this to do Brownian motion.
Okay, so it's not affecting those.
Exactly, it's not affected. Now, in other situations, if the particle is asymmetric or you make the forces different, there could be a torque that's induced, in which case you have coupling. But for the simple spherical Janus particle under the conditions I have, that's an independent equation that just is causes Brownian motion on the plane.
Sorry, the fact that you're staying close to equilibrium in the linear approximation, once you introduce the third equation, which appears uncoupled, basically implies that you're having a persistent length which is vanishing.
Is what?
Vanishing. You're working with a small persistent length for your Brownian particle. Is this equivalent?
It means that the velocity is small, but you can control the orientation time of the Brownian motion of the orientation variable. So in all of these cases, there's a certain ballistic time that appears before reorientation occurs. And so if you look at the mean square displacement, you have a ballistic component followed by a diffusive component with renormalized diffusion. But if you look in the direction of u, so if you instantaneously average along u, you can always pick out the deterministic component. Okay, so that's the first part of the story, just using the microscopic reversibility to see this component. Just a couple of quick comments on the non-equilibrium fluctuation formulas. So let me now consider the case for simplicity with no external force and look at the Langevin equation that I wrote down earlier for the rate. And corresponding to this Langevin equation, you can write down the Fokker-Planck equation. And it involves the mean reaction rate and the reaction diffusivity. That equation is easy to solve. And the solution is Gaussian, given by this form. So this is the probability that you produce n product particles in the time t, and you can see it depends on the mean reaction rate and reaction diffusivity, and trivially, if you take the ratio of producing n product molecules in time t divided by the probability of consuming n product molecules in the time t, that ratio is just given by the affinity, exponential affinity times n. So this is an example of one of these fluctuation formulas. I should note that you can also derive the more general form of the probability that the Janus particle is at position R after producing n product molecules at time t, divided by the probability that it's at minus r, having consumed end product molecules at time t, and you have an analog of the fluctuation formula for that case as well. This is a much more tricky formula to derive because you have to take into account the orientational Brownian motion, and this is derived in a situation where orientation has relaxed so that it takes its equilibrium value and then doesn't contribute to the entropy production. And you can derive this using basically large deviation theory and time-dependent versions of this using the chemical master equation as well, using large deviation theory. But I won't discuss that here.
Sorry. Isn't the exponent just the entropy production?
Pardon?
Isn't the exponent just the entropy production?
Exactly, yeah. So if you write down
So it follows from the general theory.
Exactly, yeah.
There's no need to go through details.
No, but the tricky part comes in the fact that it's an approximate form that only holds for long times. And so then you have to do some more work. Yeah, I didn't write down the entropy production formula, but for times longer than the orientational relaxation time, the entropy production takes the form you might expect, and then I immediately write this expression down. Just a comment, again, connecting back to molecular machines, you can compute the efficiency, either the chemical and mechanical efficiencies, which are the ratios of basically the power ratios in the chemical and external fields. And if you compute these quantities using the formulas that I gave earlier, you can see regimes where you can actually synthesize fuel from a product, or vice versa, or you can produce work from the chemical reaction and vice versa. I'm staring at this because it seems to have destroyed certain colors, but at any rate, there's supposed to be more colors in this picture. If you, those of you who are familiar with an old article by Julia and Pro, will see almost an identical picture for molecular machines. And it just shows that there's almost a very close analogy between these diffusio-phoretic motors and molecular machines. The difference is in the details. You have to do a lot of different work to actually get the terms, but the structure is the same for both of these cases. So there's a very nice parallel between these two cases. Okay, so just a few comments about this part. So I didn't discuss a lot. This actually took us quite a long time to do. I should say, what I've described is some work, I'll give you the reference at the end, with Pierre Gaspard, who's been looking at some of these problems, and I thought it would constitute a nice example that illustrated some of the principles here. And all of the details that go into really deriving the boundary conditions in the equations that give rise to the diffusio-phoretic velocity and the diffusio-phoretic force under various conditions. I should say that in the fluctuating thermodynamics approach, what you're doing is basically a continuum description of the environment plus fluctuations. So you're solving a Navier-Stokes equation and a reaction diffusion equation with fluctuations to describe the system, and you're coupling those fluid fields to the particle through boundary conditions. These are small particles. Micron is pretty big, but if you get down to 10 nanometers or 20 nanometers, you're starting to possibly get into some trouble. And so you don't necessarily want to test the fluctuation formula, but you definitely would like to test the conditions of the assumptions that go into the theory. And so what I'd like to now spend a few minutes on is how you can look at the systems from a more microscopic perspective in the Langevin equations that I've been describing. to now. And I'm not going to go into the details of how one does this because they're not really that important right now. The important feature is that whatever dynamics you use, whether it's full molecular dynamics or various coarse-grained versions of the dynamics, you really want to satisfy the basic physical principles. And once you satisfy those, then you can be pretty guaranteed that what you'll get out will be okay. So you want to satisfy mass, momentum, and energy in whatever your dynamical scheme is. For the dynamics, you like to preserve free space volumes. Obviously, you're going to satisfy microscopic reversibility. And if you satisfy these on long distance and time scales, you're almost guaranteed to get the hydrodynamic equations and the reaction diffusion equations out of the system. And the details of the scheme will be changes in the transport properties for these systems. And so what I'll describe are actually coarse-grained simulations where the solvent is coarse-grained, and in this coarse-grained you're replacing real collision events in the environment by effective ones, but they satisfy these properties, and so you have a faithful dynamics. So now the procedure starts by building a Janus particle, and there are many ways of doing it, but in this particular case we simply made it from beads, packed a lot of beads, linked beads, and the red ones are catalytic obviously, and the blue ones are non-catalytic, and the A and B particles are in a solvent, and they interact with the Janus particle through short-range repulsive potentials, and they undergo reversible chemical reactions. And for the dynamics, one can actually show that the reactive and non-reactive dynamics satisfy detail balance, in fact microscopic reversibility, and if you just place the Janus motor reacting in the medium at equilibrium, it will simply relax to equilibrium and stay there and not undergo any directed motion. So this is I'll just give you a picture of it. So what you see is the Janus motor, and the cloud of particles around it are just the product molecules that are being produced in the reaction. And what you don't see in the box is about 1 million solvent particles in the system. And just to show you that things are not so bad, just by looking at extracting from the simulation the velocity along the orientation direction, you find roughly 6 times 10 to the minus 4 in some dimensionless units. And if you use a continuum theory based on solving the Stokes equation and the continuum reaction diffusion equations, you find a number that's within statistical uncertainty of that result. So we also can look at the probability distribution of the number of product molecules produced in time t, and this probability distribution as a function of time, and the points are the simulation results, and you probably don't see it, but there's a solid curve that's fit through there that is the Maxwellian distribution, Gaussian distribution that you have up above, and you can extract the mean value of the number of product molecules versus time, and similarly the variance, and you can compare those to the continuum theory results, and you can see that they're quite close, indicating that for the conditions that we're considering, the continuum theory is actually, fluctuating continuum theory is actually a very good approximation. You can also test this fact that the reaction rate depends on the external force. And so the way to do this is now, in addition to applying an external force on the system, we also apply a magnetic field, and the magnetic field allows you to control the orientation of the particle as well. And so if you take the average value of the position of the particle, the z component, since we're along z, and the average value of the reaction rate, then they take this form with the given average of the orientation vector. In fact, that's almost unity because we put on a strong magnetic field on the system. And so if you look at this side, you see that the reaction rate does indeed depend on the external force. And the, for some reason I didn't put the numbers here, but the slope that you extract from the simulation agrees with the theoretically predicted slope for this case. So you can see it's got a long way to go before you actually produce fuel for the product for this particular case, and long before that, nonlinear effects occur. But in fact, you could even take this system at equilibrium and apply an external force, and then you'll actually generate either fuel or product as a result of the external force. And we've done that, and indeed you can produce fuel or product for that case. So really, you have to stay in the linear regime in order to see the effects that we predict. So I just want to say a few words towards the end. So, as I say, the statistical mechanics machinery really be used to learn something about these motors. And I've given you sort of the simplest part of it. And it's not too surprising because once you satisfy the basic laws of physics, lots of things have to come out. But it's surprising that many theories don't do that. And in fact, a lot of the experiments in this area are really not very well done, in my opinion, because they simply take a motor like this, they throw some fuel into the system, nothing is controlled, and you can't really probe the dynamics very well. And it's very easy to actually establish a steady state. I mean, one knows how from nonlinear dynamics how to establish non-equilibrium steady states. And so I think there's room for some good experiments in order to compare with some of these results. Now, if you're interested in the details of what I've described, and there are a lot of them, then these are the two articles that give them, and this is on the archive now, the microscopic simulation paper for this particular case. So before I stop, I want to make one other comment. So I picked a particularly simple example of a single Janus motor, synthetic Janus motor driven out of equilibrium. So it's an active particle, and I also gave you a very simple story of one part of the motion of the motor. This is a field where there's a lot of work going on. I would say at this particular stage, for some reason, people have skipped over some of the fundamentals and have jumped into the collective motion of many particles in the system. And there's a lot of interesting work to be done in this area, and perhaps one should really think about the basics of the underlying equations that people are using for that purpose. But I wanted to show you some of the results that you can actually find for the collective motion of these systems. So, what I'm showing you is simulations now of these sphere diameter motors, very similar to the Janus ones. And these are simulations that are done in a quasi-two-dimensional geometry. So you have three-dimensional fluid flow fields and concentration fields that we use in intermolecular potential to roughly confine the motors to a two-dimensional geometry. And this particular simulation is for motors moving forward, the way you see them, at a particular volume fraction of 0.2. So there are about 1,000 motors in this system, and I don't remember exactly, but on the order of maybe 10 million solvent particles. And the colors are terrible, much nicer on that computer, but you get a feeling for the segregation and clustering that you find in these motor systems. And so you see segregation into two phases, a gas-like phase and a clustered dense phase that's actually as a solid-like structure. And this slowly anneals and forms a large cluster, again, subject to fluctuations.
So you don't have a screening effect?
Pardon?
You don't have a screening effect due to the presence of the other particles on the surfaces, so the reaction will be reduced when you are inside the cloud.
Yeah. The answer is yes, but remember that in this particular case, I have a quasi two-dimensional layer, and so they're getting fuel from the top and bottom.
Okay.
Right. The nature of this state depends crucially on how you drive it from equilibrium and the geometry. If the motors are moving backward, all the parameters are the same, except the potentials are flipped, so that the motors move backward. You no longer get clusters, but you get strong density fluctuations in the system. And just to show you now a simulation with 6,000 motors and about 100 million solar particles, you find more or less a similar phenomenon in the system. So there's a lot of information that you can extract from these, and I've only shown you a bit of what you can do. And so this is an active area of research on active particles. Stop.
Okay, thank you. I was wondering, in the last slide you showed where you have giant number fluctuation. I mean, they are large, but they still obey the central limit theorem in that case. Since, I mean,
Which one are you talking about?
The previous slide you had.
The last fluctuations in the
You said you have typically in collective motion, when you call giant number fluctuation, you mean anomalous with respect to it. Here you should still have on the large scale normal fluctuations, right?
So this, at least on the scale that we looked at, there are anomalous fluctuations.
But if you go larger than the persistent length, you should recover.
Yeah, we weren't able to do that, so, but I would guess that that's true.
Since the only way
Because
you
your
break
equation
it, you need to break the symmetry.
Right.
To evaluate.
Okay.
I'm coming back to my earlier question because there's something physically I don't understand. So you say that on average, I mean, you say by symmetry the self-electrophoretic force must be along the axis of the particle, but this is on average. There are fluctuations. There should be fluctuations around this.
And there are.
So
we know the actual.
So why isn't the fluctuation force also picking up a contribution from the chemical reactions?
It's probably, I mean, it could be that it's only true in the linear theory, but I mean, that's
No, but you said that there was no contribution.
There is no, that's what I'm saying. So the fluctuating force in this theory is the fluctuating force that you would have in normal longitudinal.
So physically, why is it?
What? Sorry?
So physically, why is it zero? The contribution of the fluctuating force from the chemical reaction?
There is a fluctuating force due to the chemical reaction in the system. So there are two sources of fluctuations. One is the fluctuating force in the Langevin equation. There's the fluctuating force in the chemical reaction rate. The fluctuation dissipation theorem couples those two. You saw the relation.
But there's also spatial fluctuations of the chemical reaction itself, right?
Yes, there are.
So this should induce the breaking of the symmetry of the
Okay,
chemical.
so we've actually looked at that case, and if you take even a completely fully catalytic Janus particle with surface reactions, then you get fluctuations that break the symmetry, and as the particle gets larger, you can actually those fluctuations can be amplified and lead to directed motion. So that's a phenomenon that occurs on a larger scale, and so we don't see the effects of those fluctuations. Do you have a comment?
Yes, I basically also taking up this point. I mean, we have recently built a lattice model which is thermodynamically consistent beyond the linear response regime. And then when you go to the continuum limit, you can derive a Langevin equation, and then you actually find that even in the Langevin equation, you have two noise sources. One is the ordinary translational noise from the surrounding water, and then there's an additional noise from the chemical reaction which points along the director.
Yeah, so that's what I was saying. I think that in our theory, it's a linear theory.
Yes.
And this is why there's a period. In the actual phenomenon that I mentioned, we actually find those fluctuations in the simulation. And in the model that we built, the probability distribution actually depends upon the velocity of the particle. And so you actually see the coupling in that case. And what we have here, we're doing linear fluctuating thermodynamics, and this is what you find from the derivation. So I think you have to go beyond that.
We've studied the simplest version of this model where we have this sphere dimer that we call dumbbells with a self-propulsion force. We did several kinds of studies on that. The separation, also we studied fluctuation. The question is that if we have compared the results from your simulations with this more...
Yes, yeah.
Yeah.
So in...
for example, this cluster rotate, the only cluster rotate, I think, yes.
So in this paper, we do...
So the question is if there are differences between your results and the...
yes, so there are differences. So I think the models that you're referring to are the Langevin type models where you basically have the chemical gradients but not hydrodynamics in the systems. And so what we find in these cases...
You have hydrodynamics here.
We have hydrodynamics and chemistry.
Yeah.
And so the chemical gradients are by far the dominant effect that determines the clustering behavior. So clustering behavior is pretty generic for these systems. So it depends on basically slowing down the particle and reorienting fast. But there are differences that you find in the simple Langevin models compared to the full simulation. One of the most dramatic ones is that if you don't consider this type of motor, that make them the two spheres identical, so it's a symmetric case, then the simple model doesn't predict any difference between forward and backward motion. But in fact, in the full treatment of the problem, the clustering properties are completely different in those two cases. So you really have to worry about both effects coming into play in terms of determining the dynamics. But for the forward-moving motors, the phenomenological models capture a lot of the effects. In the backward-moving motors, less so.
Okay, you have a question first.